All right, one of the last lectures that I'm going to cover is a experiment type that's very common in the national exam, which usually before the national exam I actually have you guys do a lab like this, but because of, again, with the nature of what we're dealing with, we won't be able to do that. So I'm just going to kind of discuss the technique and where it is very used and useful. Now, those of you that had me in honors chemistry last year, which is almost all of you, you did a colorimetric analysis using a spectrophotometer. But I'm just going to do this again as a review leading up to the national exam. Because this has a high possibility, just like coffee cup colorimetry, very likely to be a national exam. Colorimetric analysis is another one that is very common in national exam. Now, what is it? Colorimetric analysis is analyzing a sample, its molar concentration, based on the amount of light that it absorbs. And there's found to be a relationship between the amount of light that something absorbs to its molar concentration. So some substances, let's say a copper solution. Copper, does anyone remember what copper ions in water, what color they are? For those of you that said blue, you're correct. So the more concentrated the copper in the sample is, what do you notice about the color of the solution? The more blue it is. So as the concentration gets higher and higher in copper, it's going to be darker and darker blue. And the darker it is, usually that sample will absorb more light. So there is a direct relationship between the absorbance of light that sample will do compared to its concentration. Now, the machine that I typically would run through with you guys before the national exam is called a spectrophotometer. If you need to look that up, Google it. I'm sure there'll be a couple videos on Khan Academy or Bozeman, something that aligns that you can kind of look at and see how the machine works. But in a spectrophotometer, you place a sample into the machine, and what that sample will do is we see down below. The sample will send in light of a specific wavelength. It'll travel through the sample, and that sample is usually placed in something called a cuvette. And in this case, I made the solution be red in color. Okay? A great example, that would be something like a cobalt solution. Cobalt solutions are red in color. Okay? Now, the width of the cuvette, the light traveling in at the start to the out, that is called the width of the sample, or in this case, B, the path length, which we'll see in a second in the equation. The path length is how far the light travels through the sample. What's the length of that light transmission? Outside of the cuvette, then the machine measures how much light comes out. Okay, now usually the path length is about a centimeter. Most cuvettes are about a centimeter in length, but again, that'll be told to you in the problem. So light comes in and light comes out. Now, this sample is red in a color. Would I want to send red light into the sample? The answer is no. A sample is red because what it will do is light, which contains all the wavelengths of white visible light, contains all the frequencies and wavelengths of the rainbow, all 500-600 wavelengths, all frequencies. A sample that is red, the reason why it appears red to our eyes is because it reflects red light and frequencies and wavelengths around the red spectrum the best. Because it reflects it, it really doesn't absorb it. So we want to pick a color of light that is opposite it in the color wheel. So if something is red, what color of light would you want to send through the sample? For those of you that said green, you are correct. A green, blue is okay, not the best, but a green sample would work really well because if something is red, green is about as far away from it in the color wheel as possible, and we'd want to send it. Now, the problem with purple is the fact that purple has some concepts of red and blue and mixtures of samples. Green would be the best color to use. Okay, so if you have a green sample, we would use red light. Okay, so we would send green light through the sample, and the machine, the spectrophotometer, measures how much light comes in and how much light comes out. That ratio will then, the machine will do a logarithmic function on it, and that'll compute an absorbance. So the darker or the more concentrated the sample, the more light it will absorb. And by graphing, then if I take and I do multiple concentrations, if I do multiple knowns, like down here, a 0.1 molar concentration, a 0.2 molar concentration, 0.3, as I graph that and I put it in the machine, you'll notice as the concentration increases, so does the absorbance. It ends up being a beautiful linear relationship. So then if I go ahead and sketch and use a best fit line, we will get this relationship. And this is called Beer's law. And Beer's law is this linear relationship between absorbance and concentration using colorimetric analysis. The equation, this is on your green sheet, is big A equals ABC. Big A stands for absorbance. What is the absorbance of the sample? I believe this is a big C, my fault, large C. The large C stands for concentration. And A times B, if you look at down below, this gives me a perfectly Y equals MX relationship. Absorbance on the Y, concentration on the X, which means the slope of this line is the product of A times B. So what is A and B? B, as I've already said, is the path length. This will be given to you in the problem. They will tell you the path length of the sample was 1 centimeter or 1.1 centimeters. That'll be given to you. A is called the molar absorptivity constant. It's a constant. It's based on what the substance is that's colored. Copper plus 2 has a specific molar absorptivity constant. Cobalt has a different one. Nickel. So all of these things have a specific A value associated with it. So if they ask for what is the molar absorptivity constant, you would first need to figure out the slope of the line. And then once you know the slope of the line, A would then be equal to the slope of that line that you graph divided by the path length. When you divide the slope by the path length, that'll give you the constant. And once you know the constant for it, it'll be the same number for that material no matter what lab you do on it. Okay? So down below, if I look at it, you'll notice this graph goes perfectly through the origin. Why? If there is 0 concentration, there is 0 colored species, it will absorb no light. It'll have a 0 absorption value, which should make sense. So this graph should go through the origin if you sketch it. And I'm sure, again, you won't be asked to sketch it. You'll see a graph of it on the national exam. So based on this knowledge, I don't even have to worry about knowing the A and B value because they're always the same in the material that we're using. So therefore, we get this beautiful proportionality, just like what you see with a lot of gas laws. If I know the absorbance and the concentration in one set, if I know the absorbance or concentration of a second set, I can always predict the other value. So in here, I could already complete the question mark, what I circle, without you even knowing much math. If 0.1 is 0.25 absorbance, 0.2 is 0.5, we see that as I go up by 0.1 molar concentration, I increase my absorbance by 0.25. What do you guys believe to be the value of the question mark? For those of you that said the absorbance should be 0.75, you are correct, because 0.75 over 3 is the same ratio as 0.25 over 0.1. So if you have a colorimetric problem, if I know the absorbance and concentration of one set, if I'm given a molarity or a concentration of some other value, I can easily use a proportion to figure out either the absorbance of that sample or its concentration. Let's turn the page. So in your packet, just before the page on intermolecular forces, I show you this information on Beer's law. So again, here's that graph, and here's that equation of A equals ABC, which is found on your green sheet, and there's that beautiful Beer's law plot that you can see. If I know a concentration, okay, if I have an unknown sample, I can put that sample into the machine, and what will the machine give me? It'll give me the absorbance of the unknown. If I know the absorbance of the unknown, I can then plot it and do graphical analysis, drop down to figure out what the concentration of that sample is by seeing how much light that sample absorbs. As long as I create a graph of known concentration. So if I know the sample contains cobalt, I'll make cobalt of varying concentration solutions, put them in the machine, get my beautiful linear graph, and then I can put my unknown in the machine to figure out what its concentration is. So this is how we utilize Beer's law. It's a quick, easy graphical analysis type of problem that we can use to figure out concentrations of colored substances. One other graph you might see is this one. In this graph, what they do is they vary the absorbance. They keep the same substance in the machine and they graph it. They put different wavelengths of light through the sample and they chart what that same sample, its absorbance will be at different variables. We end up getting usually a beautiful curved line that usually has one, maybe two peaks. The peak is the wavelength that we would want to utilize because this tells me the wavelength that this sample does the best job in absorbing light. So the peak, this would tell me what wavelength I should use for this material in the substance. I would not want to pick any low spot because that colored sample does not absorb that color of light very well. We'd want to pick the peak frequency. Now sometimes on the national exam, they might have a graph like this, but then they will have another, maybe they have a second substance machine which is a different color, and you chart its wavelength. So you have two different wavelengths on this machine. And they could say, what wavelength would I want to utilize to determine the black line, but not the red? What frequency or wavelength of light would I want to utilize that would maximize or be used best to confirm the amount of whatever the black line materials, maybe it's copper. I want to know the copper, but I don't want to know the cobalt. So I would want to pick a wavelength of light where I maximize the one sample, but I minimize the other sample. That would be the light I want to use, because then the red substance, whatever it is, let's say it's cobalt, will not interfere in the absorbance of the black line, which is the copper. Okay, let's say this is cobalt and this is copper. So when you see this graph, you might be asked what wavelength light should the student utilize in their experiment. You'd want to pick the wavelength of light that maximizes the one that you want to absorb and minimizes any of the other guys that you do not want it to affect the outcome of the substance you're trying to analyze. Okay, so these are two different graphs you might see. The first one is the Beer's law, where you vary the concentration. The second one is determining what wavelength of light you should utilize for the experiment. So actually graph 2 would be the first one you would do. And once you figure out the wavelength, then you'd use that wavelength to go ahead and keep that wavelength at a set value and now vary different substance solution concentrations in the machine and get your Beer's law graph. Okay? One last thing on this very page, just to kind of review, is solvation. If you guys again remember solvation, water is a polar material. Remember, it's bent. On the national exam, you might see it being good old Mickey Mouse, where the little ears are hydrogen atoms, and again showing that good old bent V shape. When we have something like sodium chloride and we put it in water, what do ionic compounds that are soluble in water do? They separate into ions. What do we call this? Dissociation. So soluble ionic compounds dissociate in water. Remember the solubility rule that you have to memorize for the national exam. Group 1, salts, ammonium NH4 salts, and nitrate salts are all soluble. Anything else that does not contain group 1, ammonium, or nitrates are not soluble, and therefore we do a KSP. Remember KSP? We do a KSP on how little bit of it does dissolve. What is that KSP value? But for things that are highly soluble, like sodium chloride in water, they completely dissociate, and when they dissociate because there's an attraction of that ion to water. And that's what we'll talk about in our next lecture when we start talking about IMFs. So what part of water is attracted to positive sodium ions? Hopefully you said oxygen. So the oxygen, which is the negative part of water, is attracted to the water, and therefore water surrounds the sodium ions, placing oxygen closer to it. And that surrounding of the water molecules of the ions is called solvation. And the more attraction there is water to the ions, the more soluble that material is, because it will have a greater amount of ions that it can support in water. So that process of solvation, remember, the negative part of water surrounds the positive ions. The positive part of water will surround the negative ions. So you want to make sure to draw the positive part of water, the hydrogen, closer to the negative ions, the negative part. And again, don't draw more than about 3 molecules is usually what they want. Put 3 water molecules around the particle ion, and that's solvation. We'll talk more about this as an IMF in our next lecture. All right, so again, solvation, just a quick review on it, and then, and again, why? Because we're looking at solutions, so copper, these substances dissolve in water having ions, and then some of these ions do cause colored solutions where we can use colorimetric analysis in Beer's law. So just a review of this concept. So if you have any questions, again, don't be afraid to shout it to me, but I just want to review these quick concepts and things you might see, because I can bet both FRQs you have on the national exam will have some type of experimental or lab component to it. All right, good luck again, and thanks for listening.